Okay, I hope you're getting an idea of the real general and wide applicability of Gaussian processes, and I hope you're not getting too freaked out by the fact we're doing things like 1 minute we're talking about latent variable models, then we're doing differential equations, and then the next minute, I don't know, whatever we're doing. But that just shows how, you know, is 4 days long enough for a summer school on Gaussian processes? Probably not, because I introduce concepts too quickly. But you know, you get an idea at least as the wide applicability. So what we did earlier is we introduced latent variable models, and then I sort of said, okay, there's a latent variable model. Oh, here's a latent force model. And that kept the mapping from latent space to data space linear. So this matrix of sensitivities, which is the sensitivity of the observation to the force, is equivalent to the mapping matrix W in the multi-output GPs. Now we're going to go in the other direction, which you already sort of spotted because you guys are now nicely trained to do that, which was we start with this model we described before, where we got to the point where we had this marginal likelihood. And you spotted, Sebastian mentioned at the front there, that that is a product of Gaussian process models where the covariance is linear. So how do we non-linearize? Well, this is easy to non-linearize by putting in a Gaussian process covariance. So that way or that way? Okay. Okay, so if we recognize that this is a product of Gaussian processes with a given covariance matrix here, we can just extend that to replace that covariance matrix with any nonlinear covariance we like. Anything we like, in fact. And that leads to what we call the Gaussian process latent variable model. So it's a very, very wide class of latent variable models. I mean, because you've seen how wide the class of covariance matrices is. So the first thing we do, though, is we obviously try our old favorite, the exponentiated quadratic. But in order to do this, all you need to be able to do is differentiate the covariance function with respect to x. So you don't need to use the exponentiated quadratic. You can use any covariance function where you can differentiate with respect to inputs. But we can't any longer solve for x via an eigenvalue problem. So in the probabilistic PCA, we just looked for x by solving an eigenvalue problem, and that was the maximum likelihood solution. Instead, we now need to find gradients of the covariance function with respect to x, alpha, and L, and sigma squared. Now, that looks like it's quite a complicated thing, but if you accept this thing I keep saying, that these independence assumptions are arbitrary. Now I wanted to, let's pause and take in a moment something. I keep saying independence assumptions are arbitrary. And we've introduced this, this model here. And I've said that this is probabilistic PCA. So that's a column of y. All rows of y, so I call that J. It's a column. Yeah? We've got independence across the feature of y instead of the data points of y. Now, the parameters here scale with the number of data points. Okay? So what I want to just pause and reflect upon is, what do you do when someone gives you a new data point? So a test point. So if I get a new test point, I don't have an x associated with that test point. Yeah, does that make sense? I have to generate a new x for that test point. So a problem with if you define your models in this way and have a parameter x which scales with n, is that every time you get an y star, a test point, you need to compute its corresponding x star. So the model is very non-parametric in that sense. But normally in Bayesian non-parametric models, we have a distribution that tells us what the new x star should be. Here, we don't. So what you have to do is you have to update your model. optimized with respect to the new observation. Do you think, well, that's one reason why people normally define models independent over P? Because what do I do here if someone gives me a new feature? So I like this sort of example. It's based on work by Charles Kemp and Josh Tenenbaum. If they have this data set of animals, and you have a set of animals that are living in the forest behind us, and then you characterize each of them by features. You say, do they have feathers or not? You know, do they have fur or not? Do they have wings, or can they fly or not? Can they swim or not? So the big frogs I see outside, you know, they don't have feathers. They can't. Or maybe they can fly. Some of them, I don't know. They don't have fur, and they can swim. You know, so you get binary values for these sort of things. And so let's say we send Maurizio out into the forest, and he finds all the animals in the forest. So there's 27. Well, it's some rich forest, so there's like 200 animals in the forest, some large number of animals, but there's a fixed number of animals in the forest, and he comes back and he's found out 10 things, 10 binary things, right? That's all the animals in the forest. Now, people have this issue with large p small n, and they say in a large p small n problem, it becomes a problem if you know too many features, right? The features become badly determined. This is the issue with a large p small n problem, because what happens is you've got only a few observations. Like if n is 5 and p is 1,000, and you use a linear model, your dimensionality of the linear parameters is like 1,000, but your n is only 5. So you don't have enough information to determine these parameters. So they call that a large p small n problem. And therefore they say it's problematic if what happens, so if Maurizio goes into the forest, he comes back, and all he tells us whether these animals can fly or not. Then we spend time building a statistical model on that, right? And we're very happy with our result. And then Maurizio is back in the forest again, and then he comes back and says, oh, good news, I found out 3 more things about all those animals, whether they've got fur, whether they've got wings, and whether they swim. And we're like, you idiot, you know, don't tell us more p, because now our parameters will become less well determined. That's an absurd thing to say. Totally absurd thing to say. Don't give me more information about the animals. You're giving me problems by giving me extra information. So you can immediately see that that's nonsensical. So if someone says large p, small n is a problem, then they've got a problem in the way they're thinking about data. But here is the solution, actually. In this model, the parameters are scaling with n, but the number of observations would also scale with n, but the number of features scales with p. And what actually happens is if we start observing the independencies across p, so now what we want is Maurizio to go into the forest and find 1,000,000 things about the animals, because p has become n. Yeah, remember that transposition I showed you in the latent variable model earlier, that we're turning everything on its side. We're now assuming independence across the features. And these lessons about parameters being well determined or not are really only based on what your independence assumption is. If your independence assumption is across features, then you have a large n small p problem. So if we observe a lot of data and very few features, then these parameters are badly determined. But if we observe very, very many, if p is enormous, if p is 25,000 and n is 3, then these x's, as long as q doesn't scale with p, become very, very well determined. Yeah? So it's all a consequence of that. But when you define the model this way round, you're in trouble when Maurizio finds a new animal. He comes back in and says, you know, there's like a furry beaver with tentacles, and I've got all its data. And I'm like, crap. Oh, now we have to find new parameters for this new animal, yeah? We can't do any predicting with that animal unless we find new parameters. But if you define your model the other way around, if Maurizio comes back with a new feature, if he comes back and says, I've now found out whether all these animals like classical music or not, right? That's trivial. We can include that in the model because it's independent across p. Just as the way we can make predictions over whether, so given like knowing one animal likes classical music, knowing that that frog likes classical music, we can predict whether the furry beaver with tentacles likes classical music or not, because we know the correlation about their behavior. The correlation is now across the animals, not across the features of the animals. Yeah? So it's just a definitional thing. And what we were doing with multi-output GPs is we were throwing this all away and saying, let's stack y to be one enormous vector, and y is one observation drawn from the world with a covariance over everything. And I think that's kind of the final, that's the ultimate thing that you should do. But in terms of, before we get there, in terms of the practical problems, if we define our model in this way, every time we observe a new animal, we need to find a new x. And that's an issue for this model here. You have to do it. The way we do it is optimizing over x given that new animal. But every new observation requires a little optimization. So I just wanted to say that. Maurizio and I were talking about that at the break, that, you know, I suspect that if you go all the way back to when people first started defining statistical models, right, they understood all these differences and why we assume independence and, you know, what it means to do this, and that you could define independence across this. And then they said, oh, but if you define independence in this way, there's a practical difficulty of when you have a new data point. So let's define independence across that way. But I suspect that they understood all the implications of what they were doing. They just said, this is the current practical thing to do given the data we have. But we've just become obsessed with models that are independent over n, and now we have all these prejudices that are focused on that world, which I don't think are true in general for modeling. And this is a model for which they're not true, but it's a model that sort of emerged kind of naturally. So this model is very good in the high data domain. Okay, so, oh, I thought, oh, where have my results gone? Right, I'm going to try and do my results. Sorry, 1 second. Because I thought I had some results actually in the... no, I know what I should do. Maurizio asked me to do this. So I'm going to do this. I thought that result was in there, but even if it isn't, I can find it. My computer's gone really slow. There's something up with my computer. It's not responding. Okay, I'm going to shut my lid and open it again. Okay, so what I want to do is I've got demos in MATLAB that I haven't actually run in a while and was trying them earlier, they're not working. But what I'd like to do instead of that is show you some work someone else did with this. Okay, that's got it. So shutting the lid and opening it again is one thing short of shutting down the machine. And hopefully my internet's going fast enough to do this. Now, this is some work a guy I've never met did using the GPLVM. And it's called Latent Doodle Space. So let me just tell you a little bit about what he's going to do in this work. I think it's my favorite application of GPLVMs. So we talked about the fact that there's no large p small n problem here. And what we're going to do is we're going to see someone who's... So most people would say is if you have a large number of features and a small number of data, don't do anything apart from a linear model. Yeah? That's the sort of common thing you hear. Don't ever go nonlinear because, you know, already you're in trouble. This is a nonlinear model where you've got 4 data points, I think there's going to be. And the data points are drawings. And this is a guy called Bill Baxter, and they did this for a Eurographics paper. So they've encoded these drawings as a vector, and that's our y. So you're visualizing a y here, yeah? So the vector is including something about, like, I don't know, the knots of the splines that form these drawings. I'm not sure how they're doing it. I haven't actually read the paper. And there's an issue because the guy draws these things separately, and there's something called a correspondence problem. Do people know about correspondence problems? So he draws 5 lines here, and he does some work which has nothing to do with the GPLVM, which is to make sure that each of these lines corresponds correctly across the data points. That's in effect making sure that the y's are in the right order. That's the correspondence problem. You don't know which column, what the identity D is of each of your y's, and you have to resolve that. Okay? So that's the correspondence problem. So he's got to solve the correspondence problem. But given he's solved the correspondence problem, he just has, each of these drawings is a high-dimensional vector, y, which we can generate. And then he models 4 drawings of this person looking in different directions. You can already see some of those drawings. And then he models a latent space, and what he's going to do is like that puppeteer from earlier, but now there's no dynamical information, it's instantaneous. He's going to move around and create new drawings. So, and you're supposed to look at these drawings and think if this is doing something natural, right? So we'll see how it does. So it's William Baxter and Kenichi Anyo, and he was at this R&D center in Japan when he did this work.
Form an important component of many different types of creative expression, such as animation. The basic idea of latent doodle space is to take a set of example drawings as input, and from those generate new drawings that are similar to the inputs.
Similar, that was. Oh, he's gonna, oh, no. Come on. I don't know why that's paused, because it's cache a load.
But unique. To demonstrate the usefulness of our technique, we have implemented a simple drawing.
Oh dear, that's going to be annoying. Let's see if we can get to this part here. So he's already done one drawing, which is hidden underneath here. It's grayed out, and he's doing another drawing over it. So the first drawing has the guy looking straight forward and has a sort of triangular mouth. Now he's got the guy looking up, and he's going to do a different mouth. He's got a circular mouth, and his nose is in a slightly different position as well. And now he's adding a third drawing. So I don't know if you can quite see the grayed out nature of it, but it's slightly, he can see the drawing underneath to help him draw the new drawing on top. And now he's going to make him look to the side. And then he does a fourth drawing that he's just sort of grayed in, making him look. So these are the 4 drawings he's got.
With a satisfactory set of drawings, we can create the latent space.
Now,
each dot on the
this correspondence problem means that it thinks some of the lines will move around, right, when it does that, because it's mapped lines to different places. So like the side of his eye becomes his nose, and you see it just move across to become the nose. And now he's fixing that up. So he's just saying, oh no, that doesn't connect like this. This connects. So look, he's just drawing the line across,
by the user interface shown here,
saying how to do that. And now he refits the model. Okay, now he's still got a problem with the nose. The nose is reversed in one of the drawings, right?
The nose. The stroke directions are reversed, which can be quickly corrected.
So he fixes that. So now he fits the model again.
Now with the stroke directions corrected, things are looking much better.
Yeah? Now I think you can agree that's a reasonable interpolation. Look at that, that's extrapolating in effect, yeah?
Now we can use the latent doodle space to implement a sort of probabilistic stamping tool.
A probabilistic stamping tool, yeah? So these are just random sort of samples from the latent space of drawings which sit on that manifold. So I think once you've seen this, you don't ever believe in large p, small n problems again, do you? I mean, it's a non-issue, I think. I mean, it's an issue, but it's an issue of model definition. It's not an issue of the data. It's a stupid thing to tell me, oh, now I've learned more about this data, so I'm in trouble. That makes no sense. As soon as you say it like that, it makes no sense. But it could cause your model problems. That's the issue. So if you've done the modeling correctly, you got problems. So here he's doing these insects. So he's doing the same thing. And now he's got a correspondence issue again. I think, yeah. Hey. So Maurizio saw one of those in the forest behind us. So he fixes that. Now, I'd like you to notice something about this. There really should be constraints on this drawing in terms of these legs should always sit on the body, right? He always puts them on the body. But the model doesn't know that. It doesn't think of them as attached. It just sees them as separate lines. So as he moves, you'll notice they're not always on the body because there's no constraint there. Yeah? So they move slightly off. He's now got his probabilistic stamping tool. Or I think actually what he does here is he clicks and moves in the latent space to create, or something like that. Or maybe he's just rotating it, I don't know. But you can imagine all sorts of fun things with this. This work's quite old now. It's about 5 or 6 years old, something like that. So we've already got more animals than we found in the forest, probably. Now I just like leaving it this bit because I like the last bit where I like this bit. Look, now he makes the I think, yeah, so it's great if you work in a field like this. Dear. Okay, so you can sort of see with very few data points, and actually he's just visualizing the mean. So bear in mind that this Gaussian process he has there, those interpolations between points, it had all sorts of beliefs about different animals. It would be interesting to like sample across those things. So he goes from this animal to that animal, but actually you could then sample an entire different various paths. He's just seeing the average expectation of what they could do. So I think this, you know, and the fact that this is all regression with, you're just trying to find the right input in some sense, yeah? So those latent spaces that you saw where the points were dropped out, he was moving in the latent space, with just what it thought were reasonable sets of inputs. And of course, when you think about it, what the model's really doing is, actually I already have this bit drawn up. It's an independent model. I mean, it's quite simple. As long as you allow yourself to transpose this matrix, it's an independent model across the columns of Y, which has just got a covariance matrix, right? So if we were to fit this model and not constrain the covariance matrix at all, it would just say that the answer is K is YY transpose. So in fact, this model only depends on inner products in those high dimensional spaces. You can re-represent the whole thing with your data set like that. And you could kernelize it if you wanted to. It'd just be hard to know what that meant. And what you're trying to do with this matrix here is make it match that in some sense, in the maximum likelihood sense. But you don't have full control over this matrix. You can only control sort of, well, you can control its elements. Alpha exponential of minus x prime. Now, I could write in the length scale, and we do keep a length scale in, but you don't even need the length scale, right? Because x and x prime can just move relatively. We do put the length scale in because I think it helps the optimizer. But you're just having to change the scale of this whole thing. And notice this is just an interpoint distance matrix. So that whole thing is rotationally invariant as well. All you're doing really is moving the latent points at a certain distance apart that it believes it's well approximating this. Now, that's one interpretation, that you've just got a funky covariance matrix, a nonlinear covariance matrix that you're trying to match to this data. And you can see that's perfectly reasonable. I've just said my covariance is not a regular covariance, it's a nonlinear function of these things. Now, because it's also a Gaussian process, though, you also have this additional interpretation that the dimensionality of these x's is important. That the dimensionality of these x's being 2 means that implicitly you're modeling the data on a 2-dimensional manifold. Yeah? 2-dimensional nonlinear manifold. It's probabilistic, not in the sense that these latent variables are probabilistic because they're optimized. They're at fixed points. It's probabilistic in the sense that the mapping. So what you have to sort of think about, the weird thing with the, and this is, I think when you think about Gaussian processes, it sort of makes sense. We have a little piece of paper. Yeah. Oh, I've got one here, look. So here's a Gaussian process.